So hello everyone. Let's start the session in a couple of minutes. Let's see if more people will be joining, and then we'll start the session in 2 minutes. Okay, let's start the session. So hello everyone, welcome you all to live session 3 of NPTEL course Fluid Flow Operations, taught by Professor Subrita Kumar Majumdar. My name is Nagvan Sai Kumar and I am the teaching assistant for this course. So last week we have discussed about fluid statics, okay, and this week we'll be going to discuss about fundamentals of flow, okay. So we'll try to understand what different type of flows that exist, like laminar flow, steady state flow, unsteady state, turbulent. So we'll try to cover all the different type of flows, and we'll also try to express fluid flow in mathematical form, okay. And we'll also be looking at different methods or different ways in which we can express fluid flow in mathematical form, okay. So starting with, we have two methods for expressing fluid flow in mathematical terms, okay. So one is Lagrangian method, and then we also have Euler's method, okay. So we'll study both these methods, yeah, okay. So we basically have two methods, okay. First one is Lagrangian method, okay. So in this Lagrangian method, so moment of each particle will be defined with respect to its location in a space and time from a fixed position, okay. So the reference point will be fixed at the start of the motion, okay. So we'll be defining moment of all the particles in the fluid with respect to its location and space and time, okay. It will be function of both space and time from a fixed position, like the reference point will be fixed and then we'll be expressing it in terms of space and time. So in Cartesian system, the position of a fluid particles in a space at any time t from its position a, b, c at time t equals 0 shall be given as. So as I've told you, it is both function of time and spatial coordinate, right? So x will be equal to function of a, b, c, that is spatial coordinates, and function of t as well, and y coordinate will be function of a, b, c again and time as well, and z will also be equal to function of a, b, c and time as well. Okay, so now this is the position of the particle. So if you want to express velocity or acceleration, so we have to take derivative of the coordinate. So u, that is velocity in x direction, will be equal to dx by or dou x by dou t. Okay, differential of x. And similarly v, that is velocity in y direction, will be equal to dou y by dou t, and velocity in z direction, that is w, will be equal to dou z by dou t. Okay, so this is about velocity. Okay, so we also have one more parameter, right? What is it? Acceleration of a body or acceleration of fluid, right? So how do we express acceleration? It is going to be differential of velocity, right? Or you can also express it in terms of displacement, but here it will be, we have to take double differentiation, right? So acceleration in x direction will be equal to ax is equal to double differential, that is dou x square by dou square x by dou t square, and ay will be dou square y by dou t square, and az will be dou square z by dou t square. Okay, so this is how you'll be expressing in Lagrangian method, and we also have a second method, that is Eulerian method. So here in Eulerian method we will describe overall flow characteristics at various points as a fluid passes through that particular point. Okay, so this means it gives various quantities such as velocity, acceleration, pressure density, etc. at any point in space and time from a purely mathematical viewpoint. Okay, so let's see how we'll be expressing velocity and acceleration in Eulerian method. So let's say we want to calculate velocity at any point x, y, z. So the velocities at any point x, y and z can be written as, so again here even in Eulerian method, so velocity will be function of time, right? Sorry, spatial coordinates and time. Okay, so if you write in terms of so if you express, so u will be equal to f1 of x, y, z, comma t. As I have told you, it is a function of both spatial coordinates and time as well. And same, sorry, this is u, and v will be equal to again function of x, y, z and t as well, and z will w, that is velocity in z direction. This will be equal to f3 of x, y, z, comma t. Okay, so the resultant or the final velocity, because it is having velocity in u, v and w or x, y, z directions, right? But the particle will be moving only in one direction, right? Okay, so the resultant velocity w will be equal to square root of u square plus v square plus w square. Okay, this will give the final velocity or resultant velocity. You can say resultant velocity. Okay, so let's say we have a three-dimensional system and particle, say this is x, y and z. Okay, this is out of this board. Okay, so let's say if particle is moving something like this in x, y, z coordinate, okay, towards outside. Okay, So it has both x, y and z coordinate. It is moving in both x, y, z and coordinates. Okay, so it will be having x component, y component and z component as well, right? Velocity. Okay, so that, but it is moving in this direction. Okay, uh, so if you resolve the components of velocity, it will be having x component velocity, y component velocity, and z component velocity as well, right? So in order to find the resultant velocity or the velocity, actual velocity of the particle with which it is moving, so we have to, this is how we will be calculating. We'll be taking squares of velocities in all the three directions. Okay, and then we'll be taking a square root. We'll add all these velocities and then we'll be taking a square root. So I think you must be aware of this when you are learning about vectors concept, right? During maybe in +1 or +2, when you're learning vectors, you must have come across this, right? Find how to find a resultant vector. Okay, so that is how we'll be doing it. Okay, so then we have lines of flow. Okay, when a fluid is flowing, let's go one by one. So first one is streamline flow. Okay, so let's say this is z, y and x. So let's say a fluid is flowing something like this. Okay, so this will be having it is y coordinate. It will be having some velocity in z direction as well, and also it will be having some velocity in x direction as well. Okay, so it will be moving with u velocity in x direction, it will be moving with w velocity in z direction, and it will be moving with v velocity in x direction, right? So coming to streamline, so streamline is nothing but a line where its tangent at each point on it indicates the direction of flow of the fluid at that point is a streamline. Okay, so let's say there's a stream of flow and suddenly there is an obstruction. So whenever there is an obstruction, there will obviously be change in the fluid flow rate. Okay, so let's take any arbitrary point. So if you're taking any point here and you're drawing a tangent here. Okay, so the direction of this tangent represents the direction of flow. Okay, that is what streamline means in simpler words. So the line where its tangent at each point on it indicates the direction of flow of a fluid at that point is a streamline. Okay, and streamline can be obtained by drawing a curve following the flow trace. Okay, and the velocity vector has no normal component. Okay, and there is no flow which crosses the streamline. Okay, so this you have to remember. This will be useful when you are solving some problems. So always remember there will be no flow across the streamline. Okay, there will be no flow across the streamline, and gradient of a streamline is dy by dx, and if a velocity component in x, y, z directions are given by u, v and z respectively, then equation for streamline can be expressed as dx by u is equal to dy by v is equal to dz by w. They will be equal. Okay. Let's take okay. So streamlines around body vary according to the relative relationship between the observer and the body. Okay, so it depends upon the reference frame. Okay, so by moving both cylinder and camera placed in the water tank at the same time, it is possible to observe relative streamlines. Okay, so if the camera is stationary, then you'll be observing with respect to the stationary observer. But if you also move the camera or point of view, then you'll be able to observe the relative streamlines. This is moving. Okay, you'll be able to observe the relative streamlines. So by moving just the cylinder, the absolute streamlines can be observed. Okay, so as I've told you, if the reference frame or the camera or the reference frame, if it is stationary, then you'll be observing absolute streamlines. But if the camera or the reference point is also moving along with this body, then you'll be able to observe the relative streamlines. Okay. So I'll just show you how relative frame lines look. So let's say if this is moving, and along with this, if camera is also moving, camera or you may call it as reference point, if that is also moving, then this is how streamlines look like. It looks something like magnetic field. When you must have learned about magnets, right? So there, when you're drawing magnetic field, it looks something like this, right? So this looks exactly similar to that. Okay, so if both observer and the body are moving, this is how it looks like. Okay, streamlines look something like this. So then we have something called stream function. Okay. We have something called stream function. Let me quickly draw a diagram. Okay, so let's consider a two-dimensional study. Always remember the conditions. Let's consider a two-dimensional study, incompressible flow, where A dash and B dash are streamlines representing the flow. Okay, so this basically represents the direction of flow. These are the streamlines which represents the direction of flow. Okay, so the flow per unit time across point A and B of two streamlines is called stream function. Okay, so this is called stream function, and the line joining AB, maybe also it can be APB or AQB. Okay, but the flow per unit time will remain the same. So it could be following any path, but the flow per unit time will be same. Let at the point A is 0, let phi, this is phi, let phi at point A is 0, then phi at point B will be flow per unit time, that is phi, it will be equal to phi, and the function phi, which is a function of x, y and t, can be defined by the amount of discharge across the coordinates as across dy. It can be written as dou phi is equal to u into dou y. So this can also be written as u is equal to dou phi by dou y. Okay, and similarly discharge across dx. So this can be written as dou phi is equal to minus v into dou x, which gives us v is equal to minus dou phi by dou x. Okay. Also note that the discharge between two streamlines will be difference in the values of stream functions. Okay. Note discharge between two streamlines will be difference in the values of the stream functions. Okay. Just a second. Is my screen visible? Okay, let me quickly share it. I think it should be visible enough. Okay. So then comes properties of a stream function. Okay, so it's also important to understand properties of a stream function as well, right? So yeah, so along a streamline, stream function will always be constant. Okay, and the rate of change of stream function will with the distance in an arbitrary direction is proportional to the component of velocity normal to that direction. Okay, and velocity vectors may be found by differentiating the stream function. Okay, so we just saw that, right? So if you differentiate the stream function, you will be getting the velocity components. Okay, so this is what it says. And then we have the algebraic sum of stream functions for two incompressible flow patterns is a stream function for the flow resulting from the superimposition of these two patterns. So which means, so if we have two stream functions and if we superimpose them, the resultant will be the superimposition of these two patterns, that is phi1 plus phi2 by ds. Okay. So we have stream stream tube and stream filament. Okay, so let me quickly draw the diagram first. Not audible. Am I audible now? Oh, sorry. So, okay, this part from. So this was clear, right? So like I was audible when I was explaining this slide, right? Okay, so this I'll repeat it again. I'll just quickly repeat it. So we have two concepts, that is stream tube and stream filament. So stream tube is nothing but a bundle of streamlines from instead of a general flow is called a stream tube. It's like a collection of uh, stream lines, okay, or bundle of stream lines, and this will be useful in analyzing the flow patterns or analyzing the flow. And these streamlines are drawn from each point of a closed curve, and which constitute a stream tube, okay. And then we have stream filament. Stream filament is defined as a stream tube whose cross section is a curve of infinitesimal dimension, okay. I'll just write it down quickly. Okay, so that's it. So stream tube is nothing but a bundle of stream lines put together, and then stream filament is nothing but a stream tube whose cross section is a curve of infinitesimal dimension. Okay, that means very small, having a very small dimension. Okay, and next we have streak line. Okay, uh, just let me draw the diagram first. Let's say we are injecting uh, particles, let's say dye particles. So they'll be flowing in a, we are introducing dye particles in a flow stream. Okay. So when you are introducing them in a flow stream, they'll be following a certain path, right? Okay. Let's mark them. So we are introducing multiple particles. Are injected into the system. Okay, so these points, so these represents multiple particles at a particular snapshot. Okay, so or positions of different particles. Okay, so a line formed by a series of fluid particles which passes a certain point in the stream, one after the other, is nothing but a streak line. Okay, so by instantaneously catching lines by injecting dye into the flow through a tip of a thin tube, so you can observe streak lines in a flow pattern. Okay, so when you are injecting the stream different particles, let's say this is a path line, and then when you are capturing different particles, just a second. So when you have different particles and when you join all these particles, this becomes a straight line. There is a fluid particle and this is called a straight line. Okay. These are the path lines. The line formed by a series of fluid particles which pass a certain point in the stream one after another. Okay. So we suppose strict line, and then we have path line and time line. I'm audible, right? Okay. Okay, I'm audible, right? Okay. So we have path line and timeline. So first, let's see path line. This is a you can say snapshot of a particle at different times. Okay, this is a snapshot of a particle at different times. Okay, so when the particle is moving in a fluid, it will be changing its position, right? So if we have a snapshot of the particle at different positions at different times, so this is how it looks. So path line is nothing but the trace of one particular particle starting from one particular point in a stream. Okay, so it is nothing but a record of it is nothing but record of path of the particle. Okay, starting from one particular point. Okay, so this is basically a path line. Okay, so we are trying to record or trace movement of particle from one particular point in a stream. Okay, so the trace of one particular particle starting from one particular point in the stream. Okay, so we can do this by recording a video. Okay, or let's say if you're releasing a balloon into the air. Okay, and if you're recording the movement of balloon in the air after releasing it, so it will be following some certain path, right? So that is nothing but a path line of that balloon. Okay, in a fluid called air. Okay, so that's how you record path lines. And then you have timeline. Okay, so timeline is generated by drawing a line through the adjacent particles in a flow at any instant of time. Is generated by drawing a line through adjacent particles in flow at any instant of time. Okay. And one more thing, in case of a steady state flow, stream, path, streak lines all are same. Okay, so we cannot distinguish between streamline, path line and streak lines. So this is important, and it is only valid in steady state flow. In the case of steady flow, streamline, path line and streak line are all the same. Okay, and then we have potential line. So the line of equal velocity potential known as potential line. Let me quickly write this. The line of equal velocity potential are known as potential lines. That's it. So these are orthogonal to streamlines. So the property of potential line is that these lines will be orthogonal to stream lines. This is also one important parameter which you should be remembering. These are orthogonal to the streamlines. And in fluid dynamics, potential flow describes the velocity field as a gradient of scalar function, that is velocity potential. Is velocity potential. And a potential flow is characterized by a irrotational velocity field. This is one more property of potential line. A potential flow is characterized by an irrotational velocity field. Applications, coming to the applications of potential flow. So this can be observed in outer flow, flow field of an aerofoils. It will be observed in water waves, electroosmotic flow, and also in groundwater flow. And potential flow theory cannot be applied for viscous internal flows. Okay. So let me quickly write down the applications of potential flow. So this is observed in outer flow field of aerofoils and water waves, electroosmotic flow, and groundwater flow. These are the real life applications of potential flow, and also potential flow cannot be applied for viscous internal flows. Viscous internal flows. Okay. Then we have velocity potential. For this, let's consider a flow. Let's consider a flow takes place in a pipeline with the pressure difference, and the direction of the flow will take place from higher pressure to lower pressure, obviously. So, thus, velocity of flow in a certain direction will depend upon the potential difference, which is a velocity potential and is denoted by phi. Velocity potential is denoted by phi. Okay. So, as per definition, dou phi is equal to u into dou x, which means u is equal to dou phi by dou x, and also so this is for x direction, and similarly for y direction also we can apply this, right? So as per definition, again dou phi will be equal to v into dou y. Okay, that is differential in that direction. So v will be equal to, that is velocity in y direction will be equal to velocity potential divided by differential of velocity potential divided by dou y. And similarly for z direction, dou phi will be equal to w into dou z, which gives us w is equal to dou phi by dou z. Okay. So now relation between potential, velocity potential and stream function. Okay. So let's write down these equations. We have u is equal to dou phi by dou x, right? And this is also equal to dou phi by dou y. Okay, using velocity potentials and stream functions, u will be equal to dou phi by dou x and dou psi by dou y. And similarly, v will be equal to dou phi by dou x, which is also equal to dou psi by dou x. This is minus. Okay, these equations are called Cauchy-Riemann equations. Okay, Cauchy-Riemann equations. So if you take sum, then d phi will be equal to dou phi by dou x into dx plus dou phi by dou y into dy. Okay. So we know that d phi will be 0 along potential line. D phi will be 0 along potential line. So therefore, dy by dx can be written as minus u by v. Okay, just divide them, you'll be getting it. And similarly, dou psi can be written as dou phi by dou x into dx plus dou phi by dou y into dou dy. Again, psi by dou psi, sorry, d psi will be equal to, differential of psi will be equal to 0 along the streamline. So we can write dy by dx as v by u. Okay, and now slope of potential line into slope of streamline will be, just multiply them. What would be the slope? Slope of potential line. This is nothing but slope, right? dy by dx. Slope of potential line into slope of streamline will be equal to -1. So you just multiply them. Y and y get cancelled out, u and u get cancelled out, and you'll be left with -1. Okay. So these are the relations between velocity potential and streamline stream functions. Okay. So now moving on to flow net. This is a graphical representation of streamlines and perpendicular equipotential lines. So let's say if we have streamlines, and then we have equipotential lines. As we have discussed, we just discussed, right? Streamlines will be potential lines will be perpendicular to the streamlines, right? So they are perpendicular, as you can see. These are streamlines. And these are potential lines. So this graphical representation is nothing but flow net. Okay. So the condition of orthogonality of streamlines and perpendicular lines is, so they are orthogonal, right? Obviously, they are, as we discussed, they are orthogonal, right? So in order to satisfy this condition, we have an equation that is dou phi by dou x into dou phi by dou psi by dou x plus dou phi by dou y into dou psi by dou y will be 0. This condition should be followed. Okay, and it is also important to analyze the flow problem in which boundary configuration and flow conditions are such that the mathematical analysis is difficult. The best example for this flow net will be flow through a Francis turbine runner. You can observe this here. Application. When you are analyzing flow through Francis turbine runner, this will be useful. So now we have different type of displacement of fluid particles. So first one is transition or translation. Okay, so element moves in the same direction. Okay, example, flow through pipes of constant diameter, and In this, pure translation does not change any stress in the element. Okay, so it will be moving along a straight line. Element moves bodily in some direction, in one particular direction. Okay, so that is, let's say if we have a body or a fluid particle in A, B, C, D location. Okay, and there is a translation motion in this, so it will be displaced to something like this: A dash, B dash, C dash, and D dash. Okay, so this is translation motion in a straight line or in a particular direction. Then we have rotational displacement. Okay, so pure rotation also does not cause any stress since there is no relative motion with respect to the rotating system. So this is something like this. So if this is a particle or fluid particle, so if it is causing rotation, then it will be moving through a certain angle. So it will be displaced through certain angle. This is pure rotation flow. And then we have distortion or deformation. Distortion or deformation. So in the first two motions there will be no stress. Okay, in these two motions no stress will be generated, but whereas in this third type of flow or that third type of displacement of fluid particles, stress will be produced. Okay, so first one is angular and the second one is linear distortion. Okay, so in angular, the particle can be moved in like two directions. Like it can be moved in counterclockwise, and it can be moved in clockwise as well. So let's say theta 1 and theta 2 are angles in which it is rotated. So theta 1 is in counterclockwise direction, and theta 2 is in clockwise direction. This is in counterclock and this is in clockwise. So let's say if the fluid particle is like this, and after rotating the body, it will be of this shape. Okay, so this is theta 1 and this is theta 2. Okay, and in linear distortion, so let's say if this is a body, initial body, and when you're deforming it in linearly, it will be of, it will be something like this. Total volume will be changed, something like elongation. Okay, so this is about this distortion or deformation. Okay, this will be angular deformation and this will be linear distortion. Okay, so these are three types of flows. One is translation flow, which is just displacement of the particle. So there will be no stresses produced in this type of flow. And the second one is rotational flow. Even in this pure rotational flow, there will be no stresses forming. But whereas in the third type of displacement of fluid, where the particle will be distorted or deformed, so we can either have an angular deformation or linear distortion. So in this, stresses will be produced. Okay, so coming to different type of flows, we can have these are different type of flows that we will be seeing, will be coming across in fluid flow operations. We will be coming across steady or unsteady state flow, which we'll be explaining in a couple of minutes. So we have steady or unsteady state flow. Then we'll be coming across uniform or non-uniform flow. Then we have developed flow. We also have compressible or incompressible flow, and viscous and inviscid flow, laminar or turbulent flow, 1, 2, 3, and dimensional flows. And then we have rotational or irrotational flow, subcritical or supercritical flow, subsonic, sonic, and supersonic flows. Okay. But before going into different type of flow patterns, let's understand few terms which are necessary for understanding those flow patterns. So first one is discharge. Okay. So what is meant by discharge? So this is nothing but a quantity of substance flowing per unit time across any cross section of a conduct is known as discharge. Okay. This is basically also referred to as rate of flow. Okay. So this can be volume, mass. This can be volume or mass of fluid. Okay. So which is flowing through a volume or mass of a fluid flowing per unit time across any cross section. Okay. So this can also be called as rate of flow. Okay. Then we have a system. So this is also one quantity that we should be aware of. So this is nothing but a portion of a fluid specifically identified for an analysis. So let's say we have a stream of flow, okay, and we want to develop an equation or something like that, or we want to analyze a particular section of a fluid. So in that case, we will be drawing an imaginary boundary. Okay, so it could be of this shape, or it could be considering only a particular section of a fluid. Okay, so this imaginary boundary separates this element from the rest of the fluid. Okay, or separates this particular section from the rest of the fluid. So this is called a system. So you must have read about system in thermodynamics, right? So we'll be defining system and surroundings, right? So similarly, a system is something which differentiate that particular section from the, or it will be separating it from the other part of the fluid. Okay. Then we have a control volume. Okay. So again, this could be a real or imaginary volume. Okay. So depending upon your analysis, it can be a real or imaginary volume, which can be defined in a problem for the purpose of easily identifying a system. Okay. This can be a real or imaginary volume section or volume, which we'll be using for defining a system. Okay. And but whereas the system is a imaginary boundary, will be defining for the particular problem. Okay. But control volume can be imaginary or a real system as well, a real volume as well. And then we have cross section. Okay. So again, a cross section, this is an imaginary surface through which the fluid flows. Imaginary surface through which fluid flows. Let's say if liquid is flowing through a pipeline. Okay. So we'll sometimes say across the cross section or something like that, right? So that means this is a some kind of imaginary surface through which the fluid is flowing. Okay. Just to identify some parameters, let's say you want to define flow rate at this particular section. Okay. Then we'll take the cross section and then we'll define how much amount of fluid is flowing through that particular cross section. Okay. So again, this is an imaginary surface. Okay. So these are the four important terms that we should be aware of when we are developing equations for fluid flow. Okay. So now let's get back to the different type of flow patterns. So as we just discussed, there are different type of flows, right? So let's understand each of them in detail. So coming to steady and unsteady state flow. So first let's understand steady state flow. Okay. So what do you understand by the word steady? First let's understand what is steady. Steady means something which is not changing, right? So it does not change some with respect to some parameter, it is not changing, right? So steady state flow is nothing but a flow whose flow state expressed by volume, pressure, density at any position does not change with time. Okay. So here we'll be using with respect to time. So that means here with respect to time, the flow is not changing. So it can be represented as dp by dt as 0, or you can also express it as dv by dt as 0. Okay. That means parameters of the flow are not changing. Pressure of this flow is not changing, velocity is not changing, or density of this flow is not changing with respect to time. Then it is called as steady state flow. And then we have unsteady state flow, which is opposite to steady state flow. Unsteady state flow. Okay. So again, unsteady state, it means the parameters are not constant, right? So the parameters are not constant with respect to what? Here we'll be considering it as time. Okay. So that means dp by dt, that is change in pressure with time, will not be 0 because pressure will be continuously changing, and velocity of the fluid or velocity of the fluid stream will not be constant, it will be changing with time. So it is unsteady state flow. Then coming to uniform and non-uniform flow. First let's understand uniform flow, and non-uniform will be exactly opposite to that, right? Okay. So again, what is uniform? So in steady state flow, steady means the parameters are not changing with respect to time, right? Whereas in uniform flow, the parameters will be constant, but now this is with respect to space or with respect to the coordinate. So it will be same at every point. So it can be changing with time. So let's say there is a flow in the system. Okay, water is flowing. Let's say this is location 1 and this is location 2. So we have two detectors here, and we are continuously monitoring the say density, volume, and we can also measure pressure, right? So we are measuring these three parameters. So here let's say P1, rho 1, V1, and this is rho 2, V2 and P2. Okay. So let's say if rho 1 is equal to P1 is equal to P2, rho 1 is equal to rho 2, and V1 is equal to V2. Okay. At any point of time, if these parameters are equal, they can be changing. Okay. So let's say at time t is equal to 0, P1 is equal to 10. Okay. And at time t is equal to let's say t seconds, after t seconds, P1 became something like 15. So units can be anything. Let's say it became 15, but these conditions are valid. So now along with P1, P2 also changed to 15. Rho 1 again, also rho 1 was initially let's say 1, and now rho 1 became 2, and V1 was around example arbitrarily let's say 2, and now V1 became say 2.5. Okay. So along with P1, rho 1 and V1, if P2, rho 2, V2 also change, that means both the variables are same at different locations, but they are changing with time. So this can happen. So that means dou V by dou S is constant. Okay, at any time, this is constant. Okay, they can be changing with time, but they should be same at every location. So then it is called as uniform flow. And exactly opposite is non-uniform flow. So dou V by dou S at t equal to t naught some time t, it will not be equal to 0. That means the parameters are changing or they are not same at each and every location. So here let's say P1 is 10 and if P2 is like let's say 20, then they're not same, right? And after t seconds this increases to 15 and this increases to 25. They're not same. They're increasing but they're not same. So then it cannot be considered as uniform flow. This is non-uniform flow. And when we are talking about steady state flow, okay, steady state flow, let's say if this is P1, this is location 1 and this is location 2. So we have same P1, V1 and row 1. We have P2, V2 and row 2. Okay. So this parameter P1 row V1 row 1 and P2 V2 row 2, they need not be equal. P1 need not be equal to P2, but the thing is, can you give a practical example of a non-uniform flow? Oh yeah, I'll come to that. So, but the thing is, P1 should be always same. Like let's say at t is equal to 0 seconds, P1 should be, let's say it is 10. But after t seconds, P1 should remain 10. It should not be changing. And similarly, P2, let's say if at t is equal to 0, it was, let's say 10 or let's say 15, it was 15, and at t is equal to t seconds, P2 became 20. It cannot be considered as steady state flow. It should remain 15. Okay. So steady state flow is represented in terms of time, whereas uniform flow or non-uniform flow, they are represented in terms of coordinates. Okay. And now coming to a practical example of non-uniform flow, let's say we have a diverging section. So we have a pipeline and we have a diverging section, something like this. Okay. So initially when the fluid is flowing here, because this is quite common, right? So we'll obviously having different pipelines, right, of different dimensions. So when we go for industries, so you will be coming across different pipelines, right? Like they have different diameters and they'll also be operated at different conditions. Okay, let's forget that. So we'll be having pipelines of different diameters. Okay, so let's say you have a unit here and you have another unit here and you want to flow fluid from this place to this place. Okay, from location 1 to location 2. So you might be using different pipelines of different dimensions, right, depending upon the requirement. So when you're using different pipelines, what happens? Area changes, right? Like the initial flow rate is constant, okay, but the diameter is changing. If diameter is changing, what parameter will be changing? V is equal to Q into A. So you'll be coming across this derivation. So flow rate will be equal to velocity into area, right? So if area is changing, what happens to velocity? Velocity will also change, right? Because flow rate is constant. So here this is A1 and this is A2. So here let's say here A1 is smaller than A2, right? So initially V1 was, this is V1 and this is V2, okay? So if area is increasing, then what happens to velocity? Velocity will obviously reduce, right? V1 will be greater than V2. So this same example you can also see it in venturimeter. So in venturimeter also you'll be, you must have done some experiments, I guess. So in venturimeter also we'll be having different cross sections. So if you are measuring, let me just draw it. Okay, so if you are measuring pressure at different locations, there will obviously be change in the pressure. Okay, that means parameter is changing with the location, right? So then it is a non-uniform flow. Okay. Oh, is it clear? Is it clear, or do I have to give one more example? Or you can also take any other example. Let's say you have a river, right? So river, when water is flowing in a river, whenever water is flowing in a river, river is not having a uniform cross section, right? It will not be a straight line, or it will not be having a uniform cross section, right? Or uniform, let's say, width of the river. This doesn't remain constant, right? Sometimes it might be a narrower space, sometimes it might be having a larger distance between the shores, right? So in that case, what happens? So the locations at which the distance between two shores is small, they will be having higher velocities. The water will be flowing at a higher speed. But whereas when the water is flowing through a channel which is having a larger area, or let's say larger distance between the shores, it will be flowing with a lower velocity. This could be one example, like a real life example where you will be able to visualize non-uniform flow. Is it clear? Is it clear, or do you want me to go through any other examples? Okay, I think someone asked me doubt, right? Do you want? Is it clear, or do you have to repeat it? Do you want me to repeat the example, or is it clear? Okay, fine. Can this video be available? Yeah, yeah. You are only getting these links, right? NPTEL will be sharing both the PPT and also video links with you, right? You will be receiving them. You must have already received them. This is third week, right? You must have already received those links, I guess. Okay. So now coming back to types of flows. So now we'll discuss about viscous and inviscid flows. So first let's discuss about viscous flows. Okay. So all fluids have viscosity, right? And if viscous effects cannot be neglected, then it is a viscous flows, viscous flow. Okay. So let's say if a particle is having, or let's say if the fluid is having a very high viscosity, and if the viscous effects cannot be neglected, in most of the cases you can neglect the viscous forces, uh, but in some cases you cannot, uh, especially in case of fluids which are having higher viscosity, you cannot neglect the viscous forces. So these type of forces, these type of flows are called viscous forces, viscous flows, sorry, and then we have inviscid flows. So this is a type of flow in which viscous forces can be completely neglected because there are some other forces which are more dominant than viscous forces. Okay, so you can completely neglect or you can completely ignore these viscous forces with no effect on the problem or solution that you are solving. Okay, so these are called inviscid flows. So if a flow in a particular flow, if viscous forces are not neglected or if you cannot neglect them because they are having a significant impact on the flow of the liquid, then they are called viscous flows. And if a flow is not affected by the viscous forces, okay, that means you can neglect the viscous forces without any effect on the flow of the fluid, then they are called inviscid flows. That's it. Like one is, in one case you have to take viscous force into account, in the other case you can neglect them without any effect on the flow of the fluid. So obviously when you are neglecting a term, then it makes easy to solve those problems, right? So let's say you have developed a mathematical equation for both the flows. So which one do you think will be easier to solve? Obviously inviscid flow will be easier to solve because you are neglecting viscous forces, right? So the problem becomes simpler. So inviscid flows are easier to solve. That too, like with respect to viscous flows. Means viscosity is 0 for inviscid flows. So it's not exactly 0, but let's say I'll give an example. We have ideal gas, right? So ideal gas is something, or ideal gas law. Ideal gas is something which is imaginary, right? There is no real concept called ideal gas, or like we don't have something called ideal gas. This is an imaginary concept. But what happens? Some gases, they tend to behave as ideal gases, right? Let's say noble gases. Noble gases, they exhibit almost similar behavior, right? So in that case, what we do, we'll neglect all the effects of real gas, right? Like let's say attraction between two molecules of same gas. Like there are some assumptions of ideal gas, right? So there should not be attraction forces between gas molecules. We have a list of assumptions, right? So as noble gases or inert gases, okay, inert gases like helium, neon, argon. So as these gases exhibit close behavior to ideal gas, we'll assume them to be uh, exhibiting ideal gas, right? So in this case, we can neglect. They'll also be having attractions, but we'll neglect them because they're not significant. Okay. So similarly, here inviscid flow as well, like there will be viscosity or there will be viscous effects as well, but there are other forces which are more dominant than viscous forces. So that is why we'll be neglecting them. It's not that viscosity is completely zero, but there are other forces which are more dominant or which are having more effect than viscosity. So in that case, we can neglect the viscous effects. Okay. I hope this is clear. Then coming to laminar and turbulent flow, this is again a different type of flow pattern. So let's take an example. Let's take a pipeline. And a fluid is flowing through this pipeline. And in this you are injecting a dye. Okay. So in a laminar flow, what happens is that the dye will be mixed slowly. Okay. It will be following the path of the liquid and it will be mixing slowly. Like there will be no rapid motion or outburst. So it will be mixing slowly, and the movement of the particle is also predictable. So let's say as soon as you inject it, you can predict that the particle will be moving in this direction. Okay. uh, and this type of flow pattern, that is turbulent and laminar, can be interpreted by something called Reynolds number. Is RE. So if RE is less than 200, or sorry, 2300, this is considered as a laminar flow, which is predictable, and also there will be slow mixing in the flow. Okay. So it is predictable, the flow is predictable. It means you can judge the direction of the flow, and also there will be slow mixing in the flow. But if you increase the velocity, or if you change other parameters, I'll come to those parameters later. Okay. If you increase the velocity or change some other parameters, what happens? This predictable nature of the fluid and also the mixing nature will be changed. Okay. So let's say when you're injecting dye into some fluid which is having higher Reynolds number, let's say 2300 to 4000. Okay. The movement of dye will not be same to that of the earlier case. Now what happens? There will be some change, some kind of outburst. So it will not be predictable, and also the mixing will be a bit rapid. So this is called transitional flow. Sorry, transitional flow. Okay. And if you slightly increase the velocity a bit more, and if the Reynolds number reaches beyond 4000, the movement of or the mixing of dye will be very rapid. Okay. So and also it will be, you cannot even predict the behavior, it will be very rapid. So this is unpredictable and rapid mixing. So if Reynolds number is more than 4000, this is called turbulent flow. So now coming back to Reynolds number. So Reynolds number is a non-dimensional number or dimensionless number. So this is given by diameter of the pipe into velocity of the fluid into density of the fluid by viscosity of the fluid. So this is also written as inertial or inertia forces by viscous forces. Okay. So the other parameters that I was talking about earlier was diameter and density and viscosity of the fluid. Okay. So let's say if you reduce the viscosity, even then Reynolds number can be increased. Okay, keeping other parameters constant. And if you decrease the density of the fluid, if you increase the density of the fluid, even in that case, you can increase the Reynolds number by keeping other terms constant. And also by changing diameter, also you can change the Reynolds number, right? So that is how you can change the Reynolds number and change the flow pattern as well. From let's say if you want rapid mixing, okay, then you can go for turbulent flow by increasing the Reynolds number beyond 4000. But let's say if you want something like laminar flow, then you can maintain the Reynolds number below 2300 and have laminar flow as well. Okay. So earlier when we were talking about inviscid and viscous forces, we said that we discussed that there are other forces which might be having a dominant role, right? So it could be inertial forces. Okay, it could also be pressure forces. Okay, like there are different forces which dominates the viscous effects. So in that case, we can neglect the viscous effects. Okay. So it exactly doesn't mean that viscosity is zero, but it means that there are other forces which are more dominant or which are affecting the flow of the pattern in a significant way. Okay. So now coming to 3, 2 and 1 dimensional flows. So firstly we'll discuss one dimensional flow. So one dimensional this laminar flow inside a pipeline always makes a parabolic curve. Parabolic curve, I didn't get you. Acha, you are talking about developed flow. Okay, okay, I forgot this. Okay, so you are talking about this flow pattern, right? So this one, right? Yeah. Haha. Laminar flow, it will be making a parabolic flow. When you increase or Reynolds number, or if you are moving from, if you're going to turbulent flow, then this will be almost same. Like it will be changing its profile from this parabolic form to something like this. Let's say this is a, sorry. Let's say if this is a pipeline and this is the flow. So in case of turbulent flow, it will be something like this. That means there is no velocity gradient at the walls. Okay. In case of laminar flow, it will be, because in laminar flow the flow rate of the liquid will be very low, right, or it will be at maintained at a low velocity, right. Then what happens, there will obviously be some drag force on the fluid, right. When the fluid is flowing, there will be obviously drag force between the surface of the pipe and the contact layer of the fluid, right. So what happens, this will be trying to push it back, okay, but the fluid will be trying to move in the forward direction. But as it does not have enough velocity or some pressure forces, so the relative velocity between at this junction or at this point will be zero. We learned this, right. So whenever the body is in contact at this junction, okay, relative velocity will be zero, right. At the point of contact, relative velocity will be zero, okay. So it will be gradually, this velocity will be gradually increasing as you move away from the surface. So that is why we will be having this parabolic form. At the center, velocity will always be maximum, but as you go towards the surface, it will gradually reach zero. That is why this parabolic profile is present, and this is mostly common in laminar flows. But when you move to turbulent flow, this will be something like this. Velocity will be almost equal at each and every junction, because there will be rapid mixing, right, and also it will be moving with a very high flow rate, right. So that is why the fluid layer which is moving, let's say this is the fluid layer which is contact with the surface, and the above layer will be moving with the higher velocity rate. So this will try to drag the lower fluid element as well with the same velocity. So in that case, it will be having a flat profile, okay, in case of a turbulent flow which is moving with a very high velocities. I hope I'm clear. Okay, so coming to one dimensional flow, so liquid will be flowing in a tube in terms of average velocity. So they'll be having only one velocity component, that is only in one direction, be it x direction, y direction, or z direction. Liquid flowing will be having only one directional velocity. So here let's take u as a function of x direction, or fluid is flowing in the x direction. Also it depends upon time, because we don't mention if this is a steady state flow or uniform flow, we don't mention anything, right. So velocity will be function of display coordinate and time as well. Depending upon the condition of the fluid, these will be changing. If it is a steady state flow, this might not be function of time, because with time it will be constant, right. Okay. Then we have 2D flow. This can be the case, or we can also have v is equal to function of y comma t, that is if the fluid is moving in y direction, and fluid can also be moving in the z direction, right. So it can be having, sorry, let's say w, z comma t. Okay, so depending upon the fluid direction, but it will be having only one component in any one direction. Okay, and coming to 2D flow, the fluid will be having two velocity components, that is it will be moving in two different planes. Okay, so here u, let's say that is velocity in x direction will be function of x comma y and temperature sorry time as well. So here we'll be having two velocities, right? So v will also be there along with this, and here it is or, because we are having only one dimensional velocity, right? So this is v is equal to v of x, y and t. Okay, this can be the case, or let's say if the fluid is moving in y and z direction, then you can have v is equal to y z t and w is equal to w into y z t, w function of y z t, or fluid can be moving in x and z direction, right? So we can have u is equal to u function of x, z and t, or w function of x, z and t. So fluid can be moving in any two planes, right? X, y, y, z or z, x. So depending on that, you will be having two different components. And coming to 3D flow, so here fluid will be having velocity component in only three directions. So it will be u is equal to u of u function of x, y, z and t, and v function of x, y, z and t, and w function of x, y, z and t. Okay. Now coming to acceleration. So what is acceleration? Same, when you are studying in physics, the definition of physics acceleration doesn't change. The same thing that we study in physics can also be applied to fluid mechanics as well, or fluid flow operations as well. Velocity is nothing but change of velocity with time, or a can be expressed as, this acceleration can be expressed as dv by dt, or it can also be expressed as double differential of displacement, right? Okay, same thing is valid here as well. So whenever we are calculating certain parameters, like let's say pressure or forces that are in the fluid motion, we need to calculate the acceleration as well, because force is nothing but mass into velocity, mass into acceleration, right? So we need to calculate acceleration as well. Okay, so consider fluid which is moving with velocity v of t as a function of time at any instant t. Okay, so now v can be written as v of x, y, z and t as a function of x, y, z and t. So now dv can be written as dou v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz plus dou v by dou t into dt. Okay, so now if you want to calculate acceleration, so it will be dv by dt. So this will be dou v by dou x into dx by dt plus dou v by dou y into dy by dt plus dou v by dou z into dz by dt plus dou v by dou t. Okay, so this is how you can calculate acceleration. Okay, and again acceleration also has three components, right? X direction, y direction and z direction, right? So when you're talking about three dimensions, ax can be written as u into dou u by dou x plus u is nothing but dx by dt. Okay, so plus v into du by dy plus w into du by dz plus du by dt. Okay, and ay can be written as u into dou v by dou x plus v into dou v by dou y plus W into dou V by dou Z plus dou V by dou T, and AZ can be written as U into dou W by dou X plus V into dou W by dou Y plus W into dou W by dou Z plus dou W plus dou W by dou T. Okay, so A will be equal to AX plus AY plus AZ, right? Okay, so this can be simply written as A is equal to dV by dt. Okay, this is also called as, so this d by dt can also be called as material derivative. Okay, and acceleration is u into dv by dx plus v into this small v, and this is capital V, where capital V is a function of x, y, and z and t, right? This is capital V by dou y, and this is small v, w into dou v by dou z plus dou v by dou t. Okay, so this is called convective acceleration. And this is called local acceleration. Okay, so similar to acceleration, similar to this concept, we can also express pressure in terms of different parameters. So let me just quickly write them down. dP by dt. This is for y coordinate, and dP by dt in y direction can be written as and in z direction you can written as okay. So then we have rotation and spinning of liquids. So visualize the flow, fluid flow as a motion of collection of fluid particles. Okay, so that deform and rotate as they travel along. So if a cube deforms but not rotate, it is called irrotational flow. If a cube does not rotate, so if cube rotates and then they possess vorticity. Okay, fluid particles running through a river flow undergoing deformation and rotation. So let's, so whenever the fluid is flowing, let's say you have an impeller and you are rotating the flow. Okay, so what happens? You'll be slowly seeing the rotational of the liquid. Okay, and as you increase the velocity, or if you increase the speed of mixing, what happens? You will be seeing vorticity forming in the liquid. It will be something like this. It will be mixing and it will be forming a vorticity because of the mixing. Okay, this is because of the spinning and rotation of the liquid. Okay, so you will also be coming across angular velocity. I think this is already explained in the class, so I will not be going into that. And then we have circulation, that is based on Stokes theorem. Okay, I think this was also explained in the class. So if you have any doubts until now, you can ask me. If not, we'll move on to doubt question session. If you have any doubts, you can ask me. You can unmute yourself and ask me or post them in the chat box as well. Anything, be it related to the problems or the concept that we just discussed. If you have any doubts, you can unmute yourself and ask me or post them in the chat box as well. Okay, so I guess we can move on to the problem session, I guess. So coming to first question, which of the following lines of flow are formed by series of particles passing through a particular or linear point in the stream? Option A, streak line; B, streamline; C, path lines; or D, timelines. Which of these following is correct? It will be option A, streak line. This is the definition of this streak line. Okay. So coming to second question, potential flow theory cannot be applied to which of these following fluids? A, irrotational flow; B, viscous internal flows; C, incompressible flows; D, all of the above. Which of these cannot be? Which of these flows cannot be? To which of these flows we cannot apply potential flow theory? We also discussed this, I guess, right? That is for viscous internal flows, option B. Okay. So coming to third question, a flow net is a graphic representation of streak lines and perpendicular path lines, streamlines and perpendicular streak lines, streamlines and path lines, streamlines and perpendicular potential lines. Okay. This also we discussed. This is a graphical representation of streamlines and their perpendicular potential lines. That is option D. Okay. Coming to fourth question, a fluid flow in the pipe of diameter D and velocity u. What will happen to the Reynolds number if the diameter of the pipe is reduced to half and the velocity is increased to 4 times of its original value? Okay, so what is Reynolds number? Rho into density into velocity into diameter by viscosity, right? So let's say R1 is RE1 is rho 1 into U1 into D1 by U2. So now, sorry, U1. So in this case, they changed diameter is reduced, right? So D2 will be D1 by 2, right? And similarly, U1 will be U2 will be 4 times of U1, right? So let's substitute it. Let's see what is R2. RE2 will be rho 2 into U2 into D2 by mu2. Okay, so density they did not change, so it will be same as rho 1, but mu2 will be, U2 will be 4 times of U1 and diameter will be D1 by 2, and viscosity also they have not changed, so it will be constant. So this will be, so rho 1 into U1 into D1 by mu1 can be written as RE1 into 4 by 2. So this will be 2 times of RE1. Okay, so that will be twice the original value, option D. Okay, so coming to fifth question, the transition from laminar to turbulent flow in a pipeline does not depend upon diameter of pipe, density of pipe, velocity of the fluid, none of the above. So what is RE? So if you want to transition from laminar to turbulent flow, that means RE should be increasing, right? So what is formula for RE? Density into velocity into, diameter into velocity into viscosity, diameter into velocity into density by viscosity. So here D is diameter of the pipe, U is velocity of the fluid, rho is density of the fluid, mu is viscosity of the fluid. Okay, so if you change diameter of the pipe, then Reynolds number will be changing. If you change velocity of the fluid, even then Reynolds number will be changing. That is, you can change it to turbulent flow. But if you change the density of the fluid, it does not have any effect, right? Because the density that we are using is density of the fluid, right? Okay, so that it does not have any effect on the flow type, or it cannot change from laminar to turbulent flow. That is, so option will be density of the pipeline. But if you change the density of the fluid, then you can change it from Reynolds number to if you change the density of the fluid, then you can change the Reynolds number and change the fluid from laminar flow to turbulent flow. Okay. So coming to sixth question, which of the following is not true regarding developed flows? Option A, the velocity profile does not change with respect to flow direction. The momentum does not change with respect to the downward stream coordinate. The flow cannot be time dependent. The pressure in the flow direction balances the shear stress at the wall. Which of this following is not true regarding a developed flow? That will be option C. Flow cannot be time dependent. Okay. So coming to seventh question, which of the following, with which type of flow does the velocity not vary at every point in the space at a given instant? Steady flow, uniform flow, potential flow, or none of the above? So it should remain remain same at each and every point. Okay, so that means it should be constant with respect to the location. So this is true for the case of uniform flow, right? That is option B. In case of large Reynolds number, large initial forces will be dominant, viscous force will be dominant, the flow will be laminar, and none of the above. So Reynolds number is large. That means it is greater than, it is having a higher number, right? So it will obviously be in turbulent flow. So it is not option C. So if RE is, what is formula for RE? Again, rho into U into D by mu, right? So this is nothing but inertia force by viscous forces, right? So that means if it is large, that means viscous force should be, initial force should be very high and viscous force should be very low. So it will be option A. Okay. What is the range of Reynolds number for transition region for a pipe, for a flow in pipe? So this is again straightforward question. That is option B. It should be between 2300 to 4000. Okay, coming to 10th question. The dash is the measure of rotation of a fluid element as it moves in a flow field. Deformation, vorticity, curl, none of the above. That will be vorticity, option B. Circulation is dash, the surface integral of velocity, the gradient of vorticity, the surface integral of vorticity, the gradient of velocity. This was explained by Professor during the session. Okay. So the correct answer will be option C, surface integral of vorticity. Coming to 12th question, the acceleration is demonstrated as dv by dt, where v is a velocity vector, and what does d by dt means? So this also we just discussed. Is it total derivative, partial derivative, material derivative, or none of the above? It is material derivative, option D, option C. Coming to 13th question, which of the following statements are not true? The angular velocity is twice the vorticity. The vorticity is 0 for irrotational flow. The vorticity is in a closed surface is 0. Closed curve is 0. All the statements are true. Which of the following is not true? That is option A. Okay. So if you have any doubts, you can post them in the chat box, or you can unmute yourself and ask me. If not, we can end this session. Any doubts which you might be having, which is a part of this session, or maybe something which you don't understand from the class? It could be related to any problem, okay? Any sum that you were trying to solve. It could be anything related to concept as well. If you have anything or any doubts, you can post them in the chat box, or you can directly ask me. You can unmute yourself and ask me. If you don't have any doubts, then you can end the session. Okay. Thank you everyone. Thank you for ending the session. Let's meet next week. Same timing 6 to 8. Okay. Thank you everyone.